All right, hello. I'm trying this lecture format now on an iPad. I don't have the fancy Apple Pencil. It's on its way, but I've got an old stylus that will work. So my writing may be a little bit slow, but nonetheless, you should be able to easily see and hear me in these videos. So on our last video, which was the March 2503 video, we talked about nucleophilic addition to aldehydes and ketones. So what we're going to do is show that today, and we're going to begin with hydrides. So hydrides contain a nucleophilic or a Lewis base hydrogen atom. So what we see there is a hydrogen with a lone pair and a negative charge. So what we're going to see in those additions of hydride to aldehydes or ketones is we're going to have what we call the group 13 hydrides. And the group 13 hydrides contain a group 13 atom with a hydrogen attached to it. So here we have a boron hydrogen bond. This would be a group 13 hydride, right? And aluminum is another example. Now, there could be other groups on the boron or the aluminum, and we still would consider this to be a group 13 hydride. The other hydrides we see are going to be group 1 hydrides, and these are hydrides attached to group 1 metals, such as potassium and sodium. These hydrides are what we consider basic hydrides. So these are going to be a Bronsted base in this case, whereas the group 13 hydrides, which we talked about here, these are going to be reducing hydrides. And these will be the ones we use in reductions of aldehydes and ketones. So let's take a look at a typical reducing agent. For the addition, for aldehydes and ketones. All right. And this is one you've already used in the laboratory, sodium borohydride, NaBH4. All right, so don't get confused. This is a group 13 hydride because the hydrogens are actually attached to the boron atom, not the sodium. The sodium is a counter ion here. It is just there to balance the charge. All right, so what we're business into this molecule is going to be the boron hydrogen bond. All right, so there's the Lewis structure of the BH4 anion, and that's what we're going to use to reduce our aldehydes or ketones. So let's take a look at an aldehyde, and we're going to take sodium borohydride, and I'm going to leave the sodium off to the side here. All right, so what we're going to see now is the attack of the BH4. And so what we're going to have is the electrons between the hydrogen and boron bond are going to donate into the carbonyl carbon. All right, so we typically see this delta plus at the carbonyl carbon, and then the electrons move up onto the oxygen. Typical pattern that we've seen over and over again, but we're showing it specifically here with the hydride addition. So what we're going to get from this process is an oxygen, and then the hydrogen has been added. All right, oops, I forgot my lone pairs up here. Put them in. All right, so this guy just coordinates to the sodium. So what we're going to have in this reaction is some kind of acid quench. So we call this H3O plus quench. And that acid quench is going to protonate the oxygen so it goes back to neutral. All right, so what do we have here? We began with, what's this up here? The beginning was an aldehyde. All right, let me see if I can cram that word in there. Oops. All right, aldehyde. And then down here we have an alcohol. All right. What kind of alcohol is this? Well, if we look at our hydroxyl group and we have our alpha carbon right there, it's attached to one more carbon group, so this is primary alcohol. So aldehydes, when they're reduced, give you a primary alcohol. Likewise, we can do this with a ketone. So the typical way that this would be written: step 1, NaBH4, step 2, H3O plus quench. And from that quenching, we get an alcohol again. But what is this? Is this primary, secondary, or tertiary? Well, let's look at the carbon. All right. OH is attached to that carbon, and that carbon has 2 alkyl groups attached to it. So this is a secondary alcohol. Right. Very good. So what we'll have here, aldehyde giving primary alcohol, ketone giving a secondary alcohol. All right. So that's addition of hydride. Very similarly, we can add what we call carbon groups through organometallics. All right. So what we're going to look at next on our list is the addition of organometallics. All right. So organometallics, we're going to look at a few different ones. There's a whole entire field of chemistry that deals with organometallics. And as you could imagine, well, what is or you can't imagine, I'm trying to tell you. What do we have here? Organo means organic, and metallic, metal. All right, so what we're going to have is an organic metal bond. All right, so one of the first ones that we typically introduce to students are the Grignard reagents, named after an organic chemist from France, Victor Grignard. All right, so this is the Grignard reagent. And what you want to think about with the Grignard reagent, all right, is that it's going to contain an alkyl group we call R, a magnesium metal atom, and then a halogen. All right, so we call these RMGX. So a typical one we could imagine would be a methyl group attached to a magnesium and then a bromine. So this would be methyl magnesium bromide. All right, so much like the hydride, where we saw the hydrogen being donated, we're going to now see a carbon bond being formed through these organometallics. So let's just take a ketone, and we'll just make 2 different R groups. And what we can do now is take methyl magnesium bromide. So I'm going to draw Me for methyl, Mg for magnesium, and then Br as my halogen. All right. So the mechanism here is that we would attack the carbonyl carbon with the the paired electrons between the methyl group and the magnesium group. So what do we get? We get an O minus again. We had an R prime here, and what did we add? We added a methyl group. All right. So now we have our 3 alkyl groups attached here, and of course we need to quench this guy. And what we're going to get here is an alcohol again. All right. So what kind of alcohol is this? Well, tertiary. So we get a tertiary alcohol. All right. So we can see we can make 3 different flavors of alcohols here, right? So going back, we can make the primary alcohol with an aldehyde and sodium borohydride. We can make a secondary alcohol from a ketone and sodium borohydride. And via the organometallics, we can take a ketone and make a tertiary alcohol. The reaction works the same if you were to begin with an aldehyde. So no need to show that. All right. So far we've covered hydride, organometallics, and the next one I want to talk about is addition of cyanide. All right. So cyanide is a very good nucleophile, as we can see, but as we have seen. However, it is quite toxic, so you need to be very careful if you choose to pursue this synthesis. Cyanide's very good chemical, but it's also very toxic, so be careful. All right, so what we're going to do is we're going to take, let's do an aldehyde this time, and what we need is sodium cyanide as our nucleophilic source, and then we need hydrogen cyanide as our acid. All right, so hydrogen cyanide is not something you just buy. That's something you have to actually make in situ. So what we typically do is we have acid in solution, all right, so HCl, for example, and we have sodium cyanide, and you can make the hydrogen cyanide in situ, all right. So what ends up happening here is we get something called a cyanohydrin. All right, so do you see where this came from? All right, we've seen this several times where we add something to the aldehyde or ketone carbonyl. We get this single CO bond, all right, and then in this case, since we're in acid, we're going to get the OH, and we've added cyanide, all right, to our carbonyl containing compound here. All right, so cyanohydrins are extremely useful synthetic intermediates. All right, so cyanohydrins can be hydrolyzed if we take acid and some heat. So we're basically going to boil it in aqueous acid. We hydrolyze the cyano group to a carboxylic acid. All right, you're saying, well, where the heck did this come from? All right, so this carbon is this carbon now. All right, so the carbon on the cyano group is now a carbon in a carboxylic acid group. So we'll see shortly in a future chapter that a cyano group or a nitrile can be hydrolyzed to give a carboxylic acid. All right, so if we look here, this carboxylic acid is kind of special because in the alpha position to that carboxylic acid, we have an OH group. All right, so this is an alpha hydroxy acid. All right, and these are very important class of molecules. You'll quite often see them in beauty supplies, chemicals, you know, like, I don't know, things that make you look younger. You guys don't have to worry about that yet, but you get the point. All right, so those things are quite useful. All right, so we can also do a reduction with lithium aluminum hydride. All right, so again, this is a hydride, all right, and the hydride is, or the hydrogens in this case, are bound to an aluminum. So this is a group 13, what we call reducing hydride. So we have our OH group there, and now what's happened is we've reduced the cyano group down to an amino group, all right? So where did all this come from? See that carbon up there on the cyanohydrin? There it is now, all right? And the nitrogen is still intact, all right? So this is an alpha hydroxy amine. And these are quite useful in neurochemistry, all right? So when we look at compounds that are active in the central nervous system, a lot of the compounds contain alpha hydroxyamine. So these are very useful for pharmaceutical synthesis. All right, we're going to go ahead and take a pause and come back with the other three reactions in a subsequent video. Thank you.